Hello, I'm Jennifer Arroyo, Editorial Director for Electronics Cooling, and I'd like to welcome you all again to our next session of Thermal Live 2020. In just a moment, you'll be hearing from Kim Fikse, Lead Sales Engineer at Advanced Cooling Technologies, who will be giving a presentation titled Advanced Thermal Techniques Across Diverse Industries. Kimberly will discuss some advanced thermal management technologies, including heat pipes and phase change material heat sinks, and offer practical real-life examples of how they are actually used to enhance cooling across a range of markets. But before we get started, I'd like to point out the Q&A panel on your screen. We invite you to ask as many questions as you like during the presentation for Kimberly to answer in our Q&A session. Also, if you would like a copy of the slides, they're available in the download section of the audience console. I'll go ahead and hand things over to Kimberly now. Welcome, Kimberly.
Thank you, Jennifer, and welcome everyone to ACT's presentation on advanced thermal management techniques. Heat is a form of energy we use every day. Once man learned how to control fire, we were able to evolve into this advanced culture. We use thermal energy to cook, keep warm, and even convert between chemical and electrical energy. But as we all know, because this is Thermal Live after all, heat in the wrong place or an unwanted place can be devastating. So in this webinar, we will explore the types of thermal challenges different markets experience, and then also analyze the best approach to overcome those thermal obstacles. So heat, being a form of energy, occurs as molecular vibration. As the substance heats up, the molecules are energized and start bouncing around. We can see this heat occur all around us. But as we said, in the wrong place, it can be catastrophic and reach a combustible state, or essentially a state of no return. Unwanted heat is typically the result of energy losses in a conversion process. So there are three different types of energy losses when you're converting energy, in the form of heat, light, and sound. But heat is the most dissipated form of energy loss. Even when we talk about efficiency, it's energy efficiency, and the losses are almost always attributed to heat. Rarely ever do we hear a loss to noise. And now another form of heat we see regularly is combustion. This is an exothermic redox chemical reaction, which means we will never be able to return back to the original state. Combustion occurs when temperatures are high enough for the reaction to take place. So the proper thermal management goal is to identify all thermal risks and ensure thermal runaway opportunities are accounted for so you never reach that state of combustion. We'll dive into the thermal challenges in 4 particular markets, starting with medical. The medical market is interesting because in some way everyone can relate and draw a level of understanding to some of the challenges. However, they are not always as apparent or something we think about when we go to the doctors. Next, we'll look into the vast and diverse defense market, with requirements that include strong, quality, rugged solutions that will guarantee performance in rough environments. Our third market is the data center industry. As many Americans were sent home to work at their kitchen table, data centers grew in necessity. And finally, we'll look into the innovative and growing electric vehicle market and address how thermal will impact its future. Our first hot topic market is the medical industry. Now, the medical industry has a very real risk when it comes to thermal challenges, primarily because the thermal issue has the potential to be life-threatening. So many of the surgical devices and the surgical tools used are rated until they hit about 109 degrees Fahrenheit. Now that's a temperature that will burn tissue. So think about it this way. A surgeon is using a drill to operate on a patient. The small motor in the drill continuously heats up during use, but after an hour of operation, the drill has reached that 109 degree Fahrenheit threshold. And so the surgeon needs to cease operation and wait for the drill to cool down. So at this point, they have a patient on the table and need to wait for a piece of equipment to cool down to the point in which it's safe to use again. Or there's the other option where the tool overheats and causes burns and tissue damage on the patient. So then you have the large amount of equipment thermal issues as well that also could lead to life-threatening concerns. Let's look at, PET scanners and CAT scanners. They require this precise image to detect any tumor or other anomalies within the body. A distortion in the image due to thermal issues could cause an error in patient diagnosis. And then you also have thermal concerns when you're looking at transporting medical material. So vaccines and other medical material require constant cool temperatures, typically around that 3 to 5 C range. When the temperatures of the shipment increase beyond 5 C, it could damage the material in the vaccines, which could cause them to spoil and therefore be unable to use on the patients they're intended for. So in this case study, we're going to actually talk more about the medical imaging tools. Now, the way these tools work is they take 3D images by taking multiple two-dimensional images or slices and rotating the machine around the body. The more sensors per slice, the better the image. Now, these sensors require temperature uniformity. The more uniform the temperature, the more in focus the image appears. And any temperature gradient will cause distortions. In order to solve this problem and to ensure that all the sensors are at that uniform temperature, we need to know all the design constraints surrounding the problem. The nice thing about the medical industry is that fairly typically you have a constant room temperature. Now, it's not always going to be that perfect 25 C ideal room temperature, but it's going to be fairly consistent around that range. Additionally, these devices can have outside heat sink controlled by liquid cooling and compressors. So now for this application, we're going to look at sensors that generate about 1.5 watts, which means the amount of heat output or waste heat as it's being used. For this, we'll look at a total number of 50 sensors aligned in a row. These sensors are going to be 3 centimeters by 3 centimeters. That 3 by 3 footprint tells us how much surface area we have to remove the heat from the sensors and about what the heat flux is. So you have 1.5 watts per 3 centimeters squared. The customer's main concerns are, can the solution provide a uniform temperature across that many sensors while also operating in a rotational speed? This is also very important because we need to look at the effects of acceleration on our thermal solution. Are we going to have acceleration forces on any liquid that we're going to apply to this? At this point, we'll want to know if there's any additional design constraints. Do we need to put it through an autoclave? Now, if it's large medical equipment, we will not need to, but that's something to look at in some of the smaller surgical equipment. Does it need to be processed or cleaned or have a serial number, and how does that apply to our actual design? For thermal challenges with temperature uniformity requirements, a heat pipe is an effective solution. A heat pipe is a passive two-phase heat transfer device that operates in a vacuum and utilizes the latent heat of vaporization to move heat from one end to the other. Now, latent heat is the amount of thermal energy required to break molecular bonds and change from one phase to another. And it is orders of magnitude higher than specific heat, which is the amount of thermal energy a substance absorbs as it raises 1 degree Celsius. In a heat pipe, the working fluid will vaporize at the hot spot, absorbing a significant amount of thermal energy, and move to the center of the pipe due to a slight pressure difference that occurs to the cooler end. At the cooler end, the working fluid will condense. That condensed fluid will return back to the hot spot via gravity or capillary action from the wick. Now, to give you an idea of how much thermal energy is absorbed, think about it this way. The latent heat of vaporization of water is 2,257 kilojoules per kilogram, while the specific heat of water is 4.187 kilojoules per kilogram degree Celsius. The reason the heat pipe is so effective at isothermalizing or temperature uniformity is because as soon as there is a temperature difference, vaporization will occur. Essentially, the heat pipe wants to reach a state of equilibrium and will continuously try to get to that state. Typically, we see about a 2 to 5 degree C delta across the length of the pipe. For the medical application, the heat pipes were embedded directly into the plate the sensors were mounted to. This plate then had a liquid-cooled interface at the edge. This cooling strategy led to a delta of 2 degrees Celsius across the sensors, which produced images with zero distortion. The thermal image on the right of this slide shows an example of heat pipes embedded into a plate with a variety of electronics directly mounted. The first image shows the application having liquid cooling on the rails, but like our CT sensors, the electronics mounted in the center of the plate were still overheating. The image on the right shows the plate with heat pipes embedded. This not only dropped the temperature of the overheating electronics, but isothermalized the plate as well, similar to the requirements of our CT scanner. Our next market is in the defense industry, specifically the Navy. In this application, we'll look at shipboard electronics. While on a ship, you are limited to the resources available on the ship itself. The ship has extremely skilled sailors who are able to identify and fix failures while at sea, but it is still important to develop a system that has the lowest risk of failure. The other challenge on board a ship is the volume restrictions. Every square inch is utilized. It is a challenge in itself to find space available for all the necessary electronics, let alone the corresponding cooling system. With space limitations come energy limitations. Ships use diesel engines to convert the chemical potential energy to the propulsion systems, life systems, and weapon systems on board. The primary goal is then to optimize the cooling solution to reduce the size, weight, and power consumption, or SWAP. Our application will use a power inverter cabinet located on the ship. Newer ships are converting to all-electric. In an all-electric ship, a diesel generator converts chemical potential energy to electric AC power. While most operation on the ship uses that AC power, systems such as the weaponry uses DC power. Therefore, inverters and additional power electronic devices are used to manage and convert the power. Our inverter cabinet will need to operate in a range of -40 to +50 degrees Celsius. Now, most power electronic devices have a case temperature rating of about 85 degrees Celsius. And the FPGAs in the inverter cabinet are typically the cause for most of the waste heat. For this application, the FPGA has a waste heat of 100 watts. And we'll also need to cool 3 FPGAs per circuit board with a total of 8 boards. So this means our cooling system must be able to remove 2.4 kilowatts of waste heat from the cabinet, while also maintaining SWAP. So once the heat is outside of the cabinet, we'll be able to cool the system with natural convection. An ideal thermal solution for this application is the loop thermosyphon because of its ability to move high amounts of heat passively. So like heat pipes, loop thermosyphon is a passive 2-phase heat transfer device that operates in a vacuum and utilizes the latent heat of vaporization to move heat from one spot to another. However, in a heat pipe, the vapor and liquid are flowing in opposite directions in the same tube. While a loop thermosyphon, the liquid and vapor flow in the same direction in separate sections of the tube. Now, the figures on the right detail the comparison between the loop thermosyphon and a typical thermosyphon. Because of this operation, the loop thermosyphon is able to transfer higher amounts of power at farther distances. There are 4 basic components of a loop thermosyphon: the evaporator body, or the hot zone, the condenser body, or the cool zone, the working fluid, and the vapor or liquid lines. It's important to note that unlike a heat pipe, the thermosyphon does not have a wick. So all of the pumping power to return the liquid back to the hot spot comes from the gravity head dictated by the design. This means that in order to have a successful loop thermosyphon design, your evaporator zone, or hotspot, must be gravitationally below the condenser. The inverter cabinet utilized the loop thermosyphon design with a custom-designed brazed aluminum evaporator to remove the heat from the FPGAs. The custom evaporator was placed in contact with all 24 FPGAs in a tight configuration to minimize space claim. The condenser, which is located outside of the cabinet, was a microchanneled aluminum plate that was ultimately cooled by natural convection in the room. This passive solution was able to keep the IGBT case temperature below 79 degrees Celsius without using any shipboard power, which maintained a lower swap. Our third market dives into data center cooling. This past year threw many of us into a strange new normal. COVID had and still has a powerful impact on our day-to-day lives. As schools and companies shifted to the remote learning and working, data centers had to gear up for the higher demand. As many may remember, the first few weeks of remote working were challenging. Internet dropped in and out, and virtual meetings struggled to keep pace. Now, as kids are back in school and remote learning has picked up, virtual calls have seen again some struggles. And this new normal may never return to what it once was. Many companies are finding success in remote work and will maintain that business model post-COVID. And with that shift in strategy, we're seeing a higher demand for these data centers' capability and reliability. Data centers are full of heat-generating components, arranged on racks, stacked in tightly packed cabinets, next to another cabinet with the same thermal load, next to another cabinet with the same thermal load, and so on and so on. They require the removal of extremely high heat loads in very tight packages. For our application study, we are addressing the high power density processors that require that high power and robust cooling solution. These processors generate a total of 4 kilowatts of waste heat in a 1U space. A U is a standard of measurement for the vertical allocation in one rack. A U is equal to 1.75 inches, which is not much at all. A typical rack is 19 inches wide, but that could vary and increase up to 42 inches in some cases. So in this application, not only was space a concern, but also weight. The project required the cooling solution to be 12 pounds or less. The optimal thermal technology here is the custom-designed ACT pumped two-phase system. Pumped two-phase is an active two-phase heat transfer device that utilizes the latent heat of vaporization. As we discussed when talking about heat pipes, leveraging latent heat allows us to remove a significant amount of thermal energy per kilogram of fluid. This means it is optimal in applications with high heat flux or high power density. The other benefit of pumped two-phase is the size. In single-phase designs, higher amounts of heat are removed by increasing the flow rate of the fluid, which requires a larger pump. But with pumped two-phase, the system is designed to interact with the component on saturation level, or essentially it's designed with a pressure that will vaporize at the desired component temperature. Because we are not increasing the temperature, we're able to remove higher amounts of heat. This gives us higher temperature control without needing a large pump. A pumped two-phase system requires 5 primary components. The low-flow liquid pump is used to circulate the refrigerant or liquid through the system. The filter is used to ensure the refrigerant is clean and lacks moisture. The cold plates are our evaporator zones. Now, a pumped two-phase system can be designed to have multiple cold plates in either parallel, series, or both. At the cold plate, the fluid boils or vaporizes, removing the heat from the hot components. The condenser plate removes the heat from the fluid, or essentially condenses and returns back to the liquid state, just like our passive solutions. An accumulator is used to store excess refrigerant and is used for volume changes in those complex designs. Typically, in pumped two-phase designs, we will use refrigerants as the working fluid, as opposed to water in some of our passive solution examples. Now, we talked a lot about the latent heat of vaporization of water being a factor in the effectiveness of heat transfer. But it's important to understand what makes a strong working fluid in a pumped two-phase design. For a passive solution, we look at the merit number. High merit number is equivalent to a strong passive working fluid and is identified by the liquid density times the surface tension times the latent heat all over the liquid viscosity. The figure on the right shows fluids with strong merit numbers. As you can see, water has an extremely high merit number compared to other common fluids. This is because of the high latent heat value and the high surface tension. For an active two-phase solution, we look at the figure of merit. The chart on the right shows working fluids with high figures of merit, or high boiling coefficients, the liquid vapor density ratios. You can see many refrigerants listed on this chart. When we applied the pump two-phase technology to the data center, we were able to design 4 cold plates in parallel that was not only able to meet the thermal requirements while still using the available air cooling to remove heat from the condenser. We were also able to increase the heat dissipation when the condenser was cooled by an additional liquid-cooled solution. The design was able to fit into that 1U by 19-inch rack and interface directly with the customer's components. Our final application investigates the rising electric vehicle industry. In this application, we will use a theoretical challenge that has yet to be thermally designed and address it with several potential advanced thermal solutions. Cooling electric vehicles is more challenging than the typical internal combustion setup. The vehicle, full of advanced electronic components, requires a higher thermal capacity and a tighter temperature control, but also has significant weight and space constraints. The vehicle also relies solely on a battery for all of its energy needs. Now, as we see the electric vehicle industry grow, we're also seeing batteries become a major limiting factor in the success of it. High-capacity batteries are essential for the electric vehicle to compete with gas IC engine vehicles. They need to be able to drive farther, longer, and maintain reliability if they want to replace an IC engine. But batteries tend to be very picky about temperature. I mean, have you ever noticed how your phone shows a low battery or shuts off when it's exposed to cold temperatures? Or on the opposite side, it'll shut off when the phone is left in the sun and gets too hot. Now, batteries directly convert chemical potential energy to electric energy during a chemical reaction. Environmental temperatures can affect the speed at which that reaction occurs. It'll slow it in cooler temperatures and increase it in warmer temperatures. It also can increase the resistivity in the conductors. So higher resistivity means higher energy losses in the form of heat. Since these factors cancel each other out, there really is a temperature zone for a battery to operate efficiently. And this will vary based on the chemical composition. So typically, a lithium-based battery will operate most efficiently in the 20C range, 20-25 C range. So an electric vehicle battery designed to hold the temperature at 25C plus or minus 5C will be able to provide a vehicle with higher efficiency and therefore a longer life. For our example, we're going to use the optimal EV battery system. So we need the vehicle to operate in any location in the world. This means the vehicle has to run in the extremely low temperatures of Alaska, Canada, and Russia. We'd also need the vehicle to run at the extreme high temperatures, upwards of 50 C. So the solution must remove the battery waste heat while also protecting it from the environmental temperature swings. And one final challenge to note is that the changing orientation and acceleration of the vehicle can affect the cooling solution. Since our passive solutions like the loop THERMOSYPHON require gravity to pump the fluid back to the evaporator, acceleration forces in a different direction could have an adverse effect on the cooling capacity. So our question here is, can a solution be designed that will hold the battery to the optimal performance temperature while operating with the variable heat loads, environment, and orientation? The first thermal technology we want to consider is the heat pipe. As we said in the beginning of this presentation, a heat pipe can be used to isothermalize several heat-generating components. A battery cell pack has rows of uniform cells with energy conversion losses in the form of heat. Battery efficiency is based on the performance of its weakest cell. If one cell is experiencing more thermal loss, it'll degrade faster than the rest and will reduce the overall efficiency of the battery. But by spreading the heat and pulling away from the poor performer, you're able to increase the battery life while still having that weak cell. ACT has embedded small 2mm heat pipes into a battery frame to not only cool down the cells, but isothermalize that system. This supported the longevity of the battery, but it still does not address our concern of thermal control in the diverse environments. Our next technology to consider is pumped two-phase. A pumped two-phase design will be able to isothermalize the cell pack, just like the heat pipes. But we'll also be able to design it to hold the system to a tight temperature range in the variety of environments. So the pumped two-phase solution would be able to heat the battery at low temperatures and efficiently remove the heat at the higher temperatures. Now, this technology, while meeting our design constraints and being optimal in the variable environment, it is very complex. Since the condenser would be affected by the environmental temperature change, control would require intricate pressure regulators. So it is my favorite and what I believe to be the future of EVs. A complex cooling solution like this is a difficult step to take in the EV design feasibility. The final technology we're going to look at is phase change material. Now, phase change material heat sinks operate as a thermal battery or thermal capacitor. They leverage the latent heat of fusion as shown on this chart to store high amounts of thermal energy over a given period of time. A PCM solution would be able to hold the battery to a distinct temperature for a longer duration. This solution, however, requires space for the PCM and adds weight to the vehicle. It also would require storage in a subambient garage for hot climates and storage in an above ambient garage for cool climates. It would essentially be charging the PCM before use, just like you're charging your battery. So if you're going to be in a hot environment, you'd want your PCM to be frozen or cooled before use. And in that cold environment, you'd want your PCM to be hot so it can heat up your battery before use. While it has benefits in the short durations and moderate climates, the long-term feasibility of a PCM solution for EV operation is questionable. In this webinar, we looked at several different types of advanced thermal management strategies and their application in a variety of markets. We identified heat pipes in the medical industry to isothermalize the row of sensors. The loop thermosyphon was used in the naval application to passively cool a high-power system. And pump two-phase was used in the data center industry to effectively cool a high heat density application in that small space claim. We also identified 3 potential strategies to cool batteries in an electric vehicle. Please stay tuned for the question and answer session. If you have questions that do not get answered, or would like to set up a meeting to talk about an application you have with our engineering team, please find us at one-act.com. Thank you.
Okay, audience, please continue to get in those questions. We'll get started. Do thermosyphons typically use different fluids than heat pipes and vapor chambers?
Hi, this is Devin Pelican. I'll answer that question. In a lot of cases, they do. The two-phase working fluids can be similar. Most commonly for loop thermosyphons, if that's what the question is referring to, we like to use refrigerants, dielectric fluids, like R134A, things that have a high liquid to vapor density ratio, like Kim was alluding to in the presentation. But you can use water, you can use other fluids, but you often have some freezing issues to worry about. Thermosyphons, unlike heat pipes, they do not have a wick structure to contain the working fluid. And so when a heat pipe freezes, you're basically just freezing the fluid inside of a sponge, and it's not bridging across the internal space of the heat pipe. So you don't have expansion issues to worry about. But in a thermosyphon, there is no structure to hold the liquid. And so you could wind up bulging your system or your pipe, and so you have to be concerned about that. So a lot of times in thermosyphons, the fluids are freeze tolerant for the application. They have high liquid to vapor density ratios. Those are some of the differences between thermosyphons and heat pipes and vapor chamber fluids.
Okay, thank you. Next, what are the most common fluids used in two-phase cooling, such as for heat pipes?
The most common fluid by far is water for heat pipes. Water heat pipes with a copper envelope are found in very many electronics cooling applications like your laptop or your computer that you're probably on right now. Another common fluid is actually ammonia. These working fluids are used for satellite and space thermal control systems. Ammonia is a good working fluid for the environment in space. It has a high vapor pressure at relatively low temperatures, which is beneficial for space applications. Some other fluids you may not have thought about are alkali metals and liquid sodium, potassium, cesium, lithium even. These are fluids that we use for high temperature heat pipes from 500 degrees C up to 1200 degrees C. These are very high temperature applications. But the working principles are the same. You still get the same high effective heat transfer rates of a heat pipe. You get isothermality and a lot of benefits that come with that. So there's a lot of working fluids to choose from for heat pipes. It just depends on what the operating temperature of the application is.
Are there any safety concerns when using a heat pipe?
It's actually the first question is a good segue to that one. So for most applications, no. The biggest safety concern for heat pipes is if you have a very large over temperature event where you could increase the internal pressure of the heat pipe to a point that fails the envelope material. For a water heat pipe, if you get up close to 200 degrees C, the internal pressure of the heat pipe could be several hundred psi, which the copper envelope may not be able to contain anymore. And then you get a small burst of mechanical stress being relieved in that situation. Other safety concerns for alkali metal heat pipes in particular, if there were ever an event where the working fluid were to egress from the envelope, alkali metals react very violently with moisture and air. And so you can wind up with a very dangerous situation if you're not taking the correct precautions when using an alkali metal heat pipe or working with alkali metals. So those are some safety concerns, but on the whole, heat pipes are very safe, very passive, very reliable heat transfer devices.
Are there any temperatures where a heat pipe will not work?
There is what is known in the industry as a bit of a no man's land for heat pipes. There are some research and development grade working fluids that are being developed, but the temperature range is somewhere between 250 and 400 degrees C. There are really no good working fluids for heat pipes that can transfer significant amount of power. Water stops around 250 degrees C, and cesium doesn't become practical until close to 400 C. And so in between those two working fluids, they're not great solutions. There are ways to work around that problem, but in general, there is a bit of a lull in that temperature range to be aware of.
Okay, thank you. Next, we have, what is the farthest distance a looped thermosyphon can transfer heat?
It's an interesting question. So loop thermosyphons, like Kim alluded to, rely on gravity head to drive the working fluid around the loop. And so the maximum distance that you can transfer that fluid depends a lot on what kind of gravity head your application can provide. And by gravity head, I'm referring to the distance, physical distance between the condenser, the cooling part of the loop, and the evaporator, the heat input part of the loop, the vertical distance. So the system is charged with the proper amount of working fluid to be able to create a column of liquid that gives you your pressure. And based on that height of that column of liquid and the density of the fluid, you can then develop a certain amount of pressure gradient in your loop. And that head, it determines everything else in the system. So if you can generate several meters of gravity separation, then you can do tens of feet or tens of meters of transfer distance. If you have a short head, then you can do short distances. So it's highly application specific. There's no hard and fast limit. It all depends on how much gravity head your system allows.
All right. Getting back to heat pipes, what is the operating pressure of water heat pipes in general?
So water heat pipes can actually be effective all the way down to, I would say, maybe, well, the freezing point physically, but they're not practical until maybe 10 degrees C to 20 degrees C, where they're actually a vacuum inside of the heat pipe. And so the heat pipe can be fully functional in a vacuum environment. So anywhere from 20 degrees C all the way up to, like I said, about 200 to 250 degrees C if you use more exotic envelope materials. Water is a good working fluid. And so that actually fits most practical electronics cooling applications, which is why water is the most universal heat pipe fluid. It's also the best in terms of latent heat and heat transfer capacity. But as you go up in temperature, the thermophysical properties of water start to fall off. And so when you get to those higher temperature ranges, the heat pipe becomes a little less effective, and you may start looking at other solutions in that regime.
Okay, well, we have a question here. How good is the jet impingement heat transfer?
It's a good question. Jet impingement heat transfer is and can be extremely efficient. In fact, it can be even more efficient if coupled with a phase change. So if you are impinging a saturated fluid onto a heated surface, you get that added benefit of the momentum of the fluid, removing heat from the surface as you impinge down on the surface, and then the latent heat absorbing that energy of the working fluid and then creating vapor or two-phase fluid in the downstream can be an extremely effective way to cool very high heat flux components. Jet impingement cooling is a more exotic, probably on the more exotic end of a cooling solution. It tends to require relatively high pressures. It requires pretty tightly toleranced components. And you also have the erosion concerns to worry about. You get a lot of your cooling in jet impingement by momentum and velocity of the fluid, and those two things also result in erosion of relatively soft materials. And so you need to be careful about how you design a system for jet impingement in terms of reliability, but it can be an extremely effective method of heat transfer in terms of heat transfer coefficient and thermal capacity.
All right. We have a question here. Are thermosyphons used in the automotive battery cooling application?
They can be. To my knowledge, there may not be many commercial applications where they are used, but most car automotive applications have a relatively fixed orientation. There's a certain incline cars can go up. It's not often that a car is going to be upside down and still needing to be cooled. So you have an orientation that would provide an advantageous situation for thermosyphons, a gravity-driven cooling system. And so if you have a battery pack, let's say, in an electric vehicle, where the battery pack is maybe in the bottom of the car, and you have cooling available above, physically above the battery pack, you can use thermosyphons or loop thermosyphons to transfer that heat from the battery pack, which is physically below your cooling solution, up to where the air may be available for cooling. So it's a good application for a thermosyphon product because you have a relatively known orientation in most cases. I just don't know that there are a lot of commercial applications that have fielded that product yet.
All right, thank you. Next, we'll move on to any maintenance needed for liquid cooling systems for telecom products.
In general, a forced liquid cooling system will require some maintenance, regardless of the application telecom, electronics cooling, data centers, anything. Active cooling systems have moving parts, and so they require some sort of maintenance. The pump is the primary source of maintenance, and also filters, depending on the type of system you're employing. You may need to routinely change some filters in the system. So almost by definition, an active cooling system will require some sort of maintenance to keep all of the physically rotating or moving components lubricated and properly serviced. Passive cooling systems like loop thermosyphons and heat pipes and vapor chambers have that advantage over active cooling systems where there are no moving parts. There's very few things to fail, and those systems can operate for tens of years without requiring any maintenance. So that's always a trade-off to be had when deciding which cooling solution is best for your application, is what level of maintenance your system is going to allow.
Okay, well, moving on back to jet impingement, we have a question. How relevant is the liquid jet impingement for cooling electronics components?
Yeah, similar to the previous question, liquid jet impingement is a way to cool localized high heat flux sources. You really need to have a high amount of energy that you're trying to remove in a very small amount of area to justify that exotic of a cooling solution, for most of the reasons I had mentioned previously. You also have some challenges of a liquid being in contact with your electronics. There are a handful of fluids that have the electrical resistive properties to be able to handle that kind of environment and not short out your system. And so those kind of considerations need to be factored in when deciding whether jet impingement is really required for your application. It's not often that it is the most practical solution, but it is a very effective solution.
Okay, moving back to automotive. How is the energy density of an electric vehicle with a heat pipe as thermal management as compared with other cooling systems?
That depends on what part of the electric vehicle this question is referring to. The battery pack I would consider a relatively low heat flux region of the electric vehicle, where other components like the power converters, IGBTs and power electronic components can be relatively high in terms of their heat density. And so heat pipes may be an effective way to remove energy from battery packs and get them out of the case so that they can be cooled more effectively. More of the power electronics side, the electric handling part of the vehicle, may require a liquid cooling solution or something more effective that can handle higher heat fluxes depending on what kind of watt density the power electronics are required to handle. There are different parts of an electric vehicle may require different levels of cooling solution, and they all need to be taken one at a time to figure out what the optimal solution is for each one.
Okay, well, we have a question here. How about graphite as a linear heat pipe?
So that wouldn't necessarily be a heat pipe. Graphite by itself would be a heat spreader. If you were to try and put a working fluid inside of a graphite envelope, that would be an interesting application, but likely challenging. Graphite or graphene maybe, by themselves can have high effective conductivities in one plane, meaning they can move heat maybe left to right, but not in and out of the material as well. And so they can be challenging materials to work with in terms of heat spreaders. But again, they're highly passive. They're solid materials. They package very nicely. They can be extremely thin and still provide high effective heat transfer rates. So like most of my answers today, it depends on the application. But it's always an interesting material to look at when packaging is a main concern.
Okay, well, that's about all the time we have for today. Thanks again to Kimberly and Devin for sharing all of that with us. All of the questions submitted will be posted on our website with answers. So even if we didn't get to your question, you'll still be able to find it there. You'll also be receiving an email with a link to the on-demand version of this presentation in about 24 hours. I'm Jennifer Arroyo with Electronics Cooling. Thanks again for participating in Thermal Live 2020.